Welcome everyone to today's recitation. We are doing chapters 4, 5, and 6. We did chapters 1, 2, and 3 last time. So together with today's problems and last time's problems, these will cover your midterm. So I would advise you to practice similar problems and also look at the problems that are in your textbooks, and that will really help you for your midterm. And again, you know the drill. If you have any questions for me, you can just mail me or send me a Teams message. Or if you are watching this live, you can just comment them down. And if you remember last time, I always suggest that after every question, I would advise you to pause so that you can try to do it yourself and work it out and then come back to the solutions. So let me just check again, making sure that I'm not on mute. Okay. So the problem 1 is from chapter 4. The problem 1 is Alex was conducting an experiment inside a hidden basement laboratory on some peculiar substance that was hoaxed to have been left behind during some recent alien visit to Earth. He found out that the temperature T of this material and entropy S are related by the following expression. Alpha S to the power P, where alpha and P are some real constants. Okay. So the question is, you need to what is the correct option regarding the heat capacity of the substance C. Okay. So the first part is C is less than 0 always. The second part is C is not less than 0 always, which is basically that C is never less than 0. C is less than 0 only when P is less than 0. And D is C is less than 0 only when P is an even multiple of I. Okay, so pause, think about it, and then come back. Okay, so hoping that you've tried to attempt. So here's the solution. So the expression that we're given is where we're going to start. We are given that T is alpha S to the power P, where S is the entropy. And if we rearrange, so rearranging, we can write this as S equals T over alpha to the power 1 over P. Okay. Now, if we differentiate this expression with respect to T, we get so ds over dt, we get P over alpha, T over alpha, 1 over P minus 1. Okay. And if we find the expression for just ds by rearranging. We just get t over alpha p minus 1 times dt. Now recall that you already have another expression for ds, and that is ds equals dq over dt, just t, and dq is c dt over t, where c is the same heat capacity that's asked in the question. Okay, so now you have two expressions for ds, and now you can simply equate them. So let's just take this to be 1, this to be 2, 1 equals 2. We get that c dt over t equal to p over alpha, t over alpha, 1 over p minus 1 dt, right? These we can cancel, and we can find the expression for heat capacity to be P over alpha, T over alpha minus 1, and we get T here. So now we have 1 minus P minus 1 power plus 1 power of T, right? So we can write this as P times T over alpha 1 over P. And from before, we know what this is. So this is our entropy. So this becomes P times entropy. Entropy. Oh, I'm so sorry. This is 1 over P. So P. Okay, let me, yes. So this is 1 over P alpha. This is 1 over P alpha. Okay, now we're good. So this just becomes S over P. Now, one important thing to note here is that we know that S, which is the entropy, is always greater than equal to 0, which means that this quantity will always, this part will always stay positive, and therefore the only way, therefore, for C to be less than 0, which means for C to be negative, P has to be negative. And that's the only way that C can be negative. So let's see if we have an option that says, and we do. So option C says that C is less than 0 only when P is less than 0. Okay. So that's your first question. Now let's move on. Problem 2, chapter 5. Okay. So 2 fixed particles, each okay, yes. So 2 fixed particles, each of charge 5 into 10 to the power minus 6 coulombs, are 24 centimeters apart. Okay. What force do they exert on a third particle of charge minus 2.5 into 10 to the power of minus 6 coulombs. That is 13 centimeters from each of them. Okay, so now pause, think, and come back. So the solution is, okay, so let's just start with picturing how this setup looks. Okay, so we assume that the two charges that are apart in the following way. Okay, and this is 24 centimeters. And now we have a third charge, so let's just call it 1, 2. The third charge is 13 centimeters from both of them. So we can draw this like this. Okay, this is the third charge. So this is 13 centimeters and this is 13 centimeters. Okay, so now we have to find, that's the question, is that what force, okay? It says what force do they exert? So for that we have to see, since let's just assume that this is x-axis and this is the y-axis. So the two charges are on x-axis and the third one is on the y-axis. Okay, so now we find the components of the two charges to find the force exerted. So the first component is along the x-axis, the second is along the y-axis. Similarly, x-axis and y-axis. Okay, so now the components that are in the x-axis cancel each other. Okay, so they don't make any difference to the force. So the first part is that x component cancel out. Okay, now we have to figure out the y component. So for that, we draw a perpendicular. Now each of these is a right angle triangle, right? We have theta here. So the y component of force, so we have two components of force. This is the Fx, this is the Fy, similarly Fx, Fy. And why I'm not calling it Fx1 and Fx2 is because they're essentially, they have the same charge. So they're essentially the same forces. So we can just add them and it'll be just twice. So total force along y will be 2k, and this 2 comes from both of these, right? 2k q q3, we're calling q1 equal q2 equal q, okay? And q3 is this one, all right? Sine theta, because it's the y component, over r square. Okay, now how do we find this sine theta? Like I said, we now have a right angle triangle. So sine theta is just perpendicular over hypotenuse. Okay, so sine theta comes out to be, so how do we find perpendicular? We use the Pythagoras theorem. So using the Pythagoras theorem, perpendicular is equal to 5 centimeters. And now sine theta is just 5 over 13. Now we substitute everything. So substitute substituting everything in Fy, we get Fy to be 301.1 newtons. Okay. Okay. Clear? Let's move on to problem number 3. Problem 3 is from chapter 6. Okay. So problem 3 says charge Q is distributed uniformly throughout an insulating sphere of radius r. Find the magnitude of the electric field at a point r/2 from the center. Okay, so a tip for y'all, if you're trying to solve a question that requires you to visualize a setup, I would suggest that you draw it so that you can look how the setup looks, and then you can solve accordingly. So let's just draw the setup for this. So it says we have a sphere. It's the center. Let's draw a sphere. Okay, and the radius of the sphere is r. Now the question says find the magnitude of the electric field at a point r/2 from the center. So if we want to find the electric field at r/2, we divide this r into two parts. This is r/2, and we draw a Gaussian surface. Okay. Now, the step 1. So let me just. Okay. So that's the setup. So step 1 of the solution is to find the charge inside the Gaussian surface. Okay, so Q inside is just rho V, and we know what the volume of a sphere is. It's 4/3 pi radius cube. Okay, and what is the radius for this Gaussian sphere? So the radius of this Gaussian sphere has the radius to be r/2, right? So 4/3 pi r/2 cube, and we get rho pi r³/6. Okay, so that's the step number 2. And now the step number 2 is we need to use Gauss's law, which is E dot dA equals Q over epsilon naught. Okay, and what is the surface area? The surface area of a sphere is 4 pi r squared, and this Q is the Q in. So Qn, now we substitute the value of Qn, which is rho pi r cube over 6. And now how do we find rho? So if you remember in the question, it says that charge Q is distributed uniformly throughout an insulating sphere. Because the charge is uniform, the density remains uniform, which means rho is equal to, so we know that Q is equal to rho V, so rho is equal to Q over V, which is Q over 4 by 3 pi r cube. Why r cube? Because now we're talking about the whole sphere. Okay, so when you substitute everything, you get that E is equal to Q over, let me just write it here. Get E equals Q over 8 pi epsilon naught r squared. Okay, and this Q is this. Okay, so that was our question number 3. Now let's move on to problem number 4. This is from chapter 4. Okay. So problem 4 is the second law of thermodynamics addresses the spontaneous direction of processes. How does this principle relate to the concept of equilibrium and the ultimate fate of the universe? Okay, so again, we have a few parts. So the first part is equilibrium is the result of violating the second law, leading to the destruction of the universe. The second part says the second law ensures that equilibrium is never achieved, causing constant changes in the universe. The third part says that the concept of equilibrium is unrelated to the second law. It is an artifact of theoretical models. Part D says the second law predicts that the universe will eventually reach equilibrium, resulting in heat death. And part E says that equilibrium and the second law are theoretical constructs unrelated to the dynamics of the universe. Okay. So pause, think about it, and then come back. Okay. I hope you had some time to think about it, and now let's find out what the correct answer is. Okay, so the correct answer to this question is part D. The second law predicts that the universe will eventually reach equilibrium, resulting in heat death. Excuse me. Okay, so let me just write down a few words to explain this. So according to the second law, the universe tends towards a state of maximum entropy. Now, if you remember, in one of our previous questions, we talked about how entropy is always greater than equal to 0, right? So the universe tends towards a state of maximum entropy where all energy is uniformly distributed and no more useful work can be extracted. And this state is known as heat death, where the universe reaches thermal equilibrium and processes come to a halt. Okay, so let's move forward to problem number 5. This is from chapter 5. So 2-point charges of charge 8q and minus 2q are located at x equals 0 and x equals L, respectively. The point on the x-axis, so you have to find at what point on the x-axis does the net electric field become 0 due to the charges. Okay, so what this means is, so let's just first draw how this setup looks. So this is our y-axis, this is our x-axis, okay, and it says that charge of 8q is at x equals 0, which is this. Let's just call it 1. And the second one is at L. So let's just call this point L, distance from the origin. And this is minus 2q. Let's just call it 2. Okay. Now we have to find at what point does the net charge become 0. So let's just assume that that is some point x distance from the origin. What this means is that at this point, both the charges will be equal to each other. And since this is negative, this is positive, the net electric field will be 0. So the electric field equation is, we all know, kq over r squared. Okay, so we have k 8q over, so now instead of 0, we want to find the electric field at point x. So that becomes x squared, and the other one becomes k 2q over L minus x squared. So the distance, this, if you want to find for here, is L minus x. So we get this distance. Okay, this is what we have to find. This is L minus x. Okay, now we just have to do the algebra now, and this becomes this 1, 4, and now this is x squared equals 4l minus x the whole square. This becomes 4l squared plus 4x squared minus 8lx equals x squared. So this becomes a quadratic equation, which is 3x squared minus 8lx plus 4l squared equals 0. Now you can find using the square root equation, but this, if you look at this equation, this looks a little easier than that. So what we can do is we can divide this minus 8lx into two parts such that both the parts, when you add it together, it gives you minus 8lx, and the coefficient of those two when you multiply gives the same multiplication of this. Okay, so what I mean is I can write this as 6lx, right, and minus 2lx. So I just divided minus 8lx into minus 6lx minus 2lx plus 4lx squared. Okay, why did I do that? Now, just consider the first part, just this part, okay? And consider this separately. So this becomes, what we can take out common is 3x. This becomes x minus 2l, right? And this becomes, we take out minus 2l. So this becomes x minus 2l. We can write this as 3x minus 2l, x minus 2l. So this gives us two solutions, which is 3x minus 2l equals 0, giving x equals 2l over 3. And the other one is x minus 2l equals 0, x equals 2l. So the two solutions that you got is this one and this one. So both at distance 2l and 2l over 3, the net electric field will be 0. Okay. So now we have the last question for today. Okay. Problem 6 from chapter 6. Okay. So the question is, an electron is placed at a distance of L over 2 just above the center of a square or of a cube of edge L. Find the magnitude of the electric flux that passes through the square. Okay, so again, like last time, we will draw how that looks. Now we have a cube. Okay, now this is L, all the edges are L, and let's just take that this is the center. So right above the center, so now imagine this to be a square. This is the center and this is L. So right above the center becomes this, and it's L over 2, so it just becomes this, right? Because this is L, which means this is L, and this is center, so this is L over 2 distance. So let's just assume it's somewhere here. Okay, so we have an electron here. Now we have to find the magnitude of the electric flux. Okay, so we know what electric flux is. Electric flux is just phi q inside or q enclosed over epsilon naught. Okay, and then if we want to find total flux that passes through the square, then so this flux is the total flux in the cube. Now if we want to find the flux that passes through this square, then we have to divide this flux by 6 to get for one edge. Okay, and now how do we find that? So first we have to find Q enclosed, which is just the charge enclosed. So what's the charge? It's just one electron. So charge of one electron is 1.6 into 10 to the power minus 19 coulomb. And we have epsilon naught to be 8.85 to 10 to the power minus 12 coulomb square Newton per meter square. Okay, so our phi is 1.6 to 10 to the power minus 7, or 8.85. And we have coulomb here. We have coulomb square. Newton per meter square comes here. So this just becomes coulomb per Newton meter square. Okay. Oh, it's just Newton meter square over coulomb. Okay. Now to find the flux around one square, which is one edge, we just take this, divide by 6, and the answer comes out to be 3.0 into 10 to the power minus 9 Newton meter square per coulomb. And that is your answer. Okay, and that is for today. See you next time. Bye.